This is FRM Part 1, Book 2, Quantitative Analysis, Chapter 7, Regression with a Single Regressor. And this chapter really could be called, let's just extend what we talked about in Chapter 6. So let's get right to the learning objectives. We're going to take a look at some confidence intervals for regression coefficients, look at p-values, interpret the hypothesis about those regression coefficients. We've got to worry about some of the assumptions underlying the ordinary least squares regression model, which in this chapter focuses on the difference between homoskedasticity, which was the original OLS assumption that we talked about last chapter, and then its counterparty heteroskedasticity. And we'll talk about when those two exist. We need to concern ourselves about the OLS estimators. Are they blue? I'll tell you about blue in a later slide. And then look at the Gauss-Markov theorem and then do a test statistic, which we've done a number of times. So some of this stuff is going to be a little bit of a review, and then there's going to be some new and important stuff together. So let's do a quick recap. Let's look at a simple linear regression model where we have the dependent variable over on the left-hand side of the equal sign. We'll call that y. It's also known as the predicted variable. And then the independent or the explanatory variable is over on the right-hand side of the equal sign. So think about what we're doing. We're trying to take the x variables and use x to explain and, in fact, predict y. We do this through a process of ordinary least squares, and so notice there is a beta 0 and a beta 1 in this regression equation, and those are the regression parameters, which are unknown. So we need to kind of figure out what they are. That's what regression analysis does. And then we have that error term way out on the right, and the expected value of that error term is going to be 0. But we have to have that error term in there because x is never going to perfectly explain y. So we need to figure out what else is out there or how big is that error term. All right, so this is what we do here. We have this fundamental economic relationship between two variables. So we formulate a regression model. There's the y and the x, and the unknown parameters are beta 0 and beta 1. Then we go out and collect the sample data. We get all of the x's and we get all of the y's. I think in the previous chapter, we were looking at an example that included interest rates as our x variable and changes in GDP as our y variable. And we get together and we decide, are we going to use Excel, or are we going to use SPSS or Minitab or some kind of a software program to estimate the regression equation, and then that regression output will give us beta hat 0 and beta hat 1. That's the intercept and the slope coefficient. And by the way, when I was in graduate school, I always thought it was really silly when my econometrics professor used to say the words beta hat, beta hat. It just didn't sound very graduate school kind of language with a hat. But clearly you can see on top of it, it's a hat. I don't know what else you could call it. And then finally, we're going to use those estimated parameters to provide us estimates of the true parts of the model. All right, so here's the question then. We can go back. So let me go back here to that formula. Look at the what is that, a blue egg on the bottom right? You know, there's our regression equation, and we then can have the regression output. And what we want to do is we want to say, okay, does the slope coefficient mean anything to us? I mean, in other words, if we were trying to predict the performance of my sons on their German tests, and we're using the number of times that I shoveled snow during this past winter, we can run that. I can collect data and run a regression equation and estimate a set of linear parameters, and I can get some number for beta 1, but it doesn't really have any meaning. So we need to ask ourselves the question, is it economically significant, which in my example with the tests and the snow shoveling, of course that's not. But if I'm going to do interest rates and changes in GDP, I'm going to get an estimate for beta 1. I need to know if it's statistically significant. Now, what we say that is that if that slope coefficient is equal to 0, then it's insignificant. And that should make perfect sense because, I mean, let's think about it. If the slope is 0, that must mean that x, like interest rates or snow shoveling, has no impact on my children's German grades or changes in GDP. If it's not equal to 0, then we say that it's significant. But we need to determine statistical significance. And that can only be the result of some statistical test that we can conduct around that slope coefficient. All right, 3 ways to do this. We're going to use critical values, we're going to use p-values, and we're going to use confidence intervals. All right, let's go ahead and state the null hypothesis. All right, so what you do is you create the null hypothesis as if you want the test to fail the null hypothesis. So with interest rates and with changes in GDP, our null hypothesis is that interest rates have no impact on GDP. Notice to the right of the top blue box, X does not affect Y. The alternative hypothesis is the rationale for the economics and the fundamentals of the creation of our original model, which says that, okay, beta 1 is not equal to 0, might be greater than, might be less than. Remember, that slope coefficient could be positive or negative. And what we conclude is that X then will affect Y. Now, if we go back and run this test on my children's grades and snow shoveling, we're pretty sure that pretty certain that we're going to say, you know what, the null hypothesis is correct. Snow shoveling has nothing to do with test performance. But with inflation and GDP, we need to compute the test statistic. And that's what we do in step 2 there. So note we have beta hat sub 1, and then we subtract in the numerator the value of the null hypothesis, which is going to be 0, and then we divide by the standard error. Remember, we're always dividing by some measure of variability to standardize this stuff. Then what we're going to do is get our tables out. We love looking at those tables. We spent lots of time in the previous chapter or so. Remember differentiating between the Z table, which is for really, really large samples, and then the T table, which is for samples that are less than 30. And then also remember about when we did this in the last chapter, we had to worry about whether the variance of the population was known or unknown. That's less important here. This is going to be the T distribution with n-2 degrees of freedom, and that's because there are 2 unknown parameters that have to be estimated. So there's a great picture of the normal distribution. And what we're trying to do is we're trying to formulate a test so that if in fact X does not predict Y, it'll fall inside of that light non-rejection region. But if we're going to reject, and notice there's a rejection region out to the right and a rejection region out to the left, which is a 2-tailed test. You always do a 2-tailed test in I shouldn't say that. Most of the time you do a 2-tailed test when you're performing regression analysis. Now, the p-value is the smallest level of significance at which we can reject the null hypothesis. And so I want you to think about the alpha that we've talked about over the last couple of chapters. Alpha is some measure of our level of significance, like 1% or 5%. So if the P falls below, let's just pick 5%. If it falls below that, then we can reject the null hypothesis. All right, let's go take a look at an example here. We're trying to predict the price of a share of stock. So we get a slope coefficient is 0.6. Standard error is 0.25. Sample has 30 observations, so we're going to determine if the estimated slope coefficient of 0.6 is significantly different from 0. Now, what I want you to do is I want you to look just quickly at step 2. I want to give you kind of a big picture thing here. So look at that formula. We got 0.6 minus 0 over 0.25. So when is that number going to look an awful lot like 0? The 0.6 is the estimate, right? And 0.25 is the estimate of variability. what would force that number to look like 0 or be some number around 0? Well, the only way that it can be somewhere around 0 is if that denominator is a big number. I mean, suppose the standard error of this regression model were 25, not 0.25. Well, then that test statistic would be way smaller and it would be closer to 0. So really what we're doing here is we're looking at the relationship between the slope coefficient and its and some measure of risk, some measure of variability. Okay, if the variability is smaller, then we have a greater likelihood. All right, so let's go work through the steps here. Step 1, state the hypothesis. That's that the null hypothesis is that beta 1 is equal to 0. Alternative is that it is not equal to 0. We can easily compute that test statistic from the results of the regression output that was on the previous page. Then we get out our t-value, so we look this number up. So we've got, we're going to do 95%, so we're going to put 2.5% in the left and 2.5% in the right tails. We look up 28 degrees of freedom, and we get a critical value of 2.048. So note the green line going down the middle of the normal distribution picture of the bell-shaped curve. That thing is going to be 0, so we put that all the way out there to 2.048. Our test statistic, it lies to the right of that. All right, so what do? We reject the null hypothesis, and we say that the slope coefficient is statistically significant. How about if we use the p-value approach? We're going to do the same couple of first steps. State the hypotheses, compute the test statistic, and then to kind of take a shortcut here, we're going to apply the central limit theorem, which says that, most distributions approach a normal distribution. And the t with 28, we're going to kind of do a little bit of rounding here, but that's not going to matter. And so we're looking for the probability that a z is going to be greater than 2.4. And we look up this look up 2.4 on the z table. So remember, run your finger down to 2.0 and then run your finger over to 0.4, and you get the 99.18, and that's if you're looking at the entire z table. If you're only looking at half, then you're going to have to add 50.5 to the 4918. We get the 0082, multiply that by 2 because we're throwing it into both tails, and that's 1.64%. So our p-value is 1.64%, which is less than 5%. So we're going to reject the null hypothesis again. So we reject here using the critical value method. We reject it here using the p-value method. That brings us to this third method. Let's look at the confidence intervals. And remember that I talked about confidence intervals in the previous chapter, and what we're really thinking of is just a range. I always ask my children, I said this in the previous chapter, what grade do you think you made? What's the highest and what's the lowest? So a confidence interval just gives us a range. But unlike my children who took a German test last week, and I asked them what they made, and they both said, probably about a 90. And I said, what's the highest and lowest? And one said, the lowest I made was 85. The highest I made was 90. And the other one said, well, I might have made an 80, but I could have made a 95. So, this is just the way their 14-year-old brains kind of work. But here, with a confidence interval with a regression analysis, we need to do this from a statistical perspective. So we need to use critical values from the table, and we need to use standard errors. So there's the point estimate, beta hat 1. Then we're going to add and subtract. So there we have the plus or minus. And all we're going to do is plus or minus the critical value times that standard error. So think about my children's estimate of a 90. They're going to do plus or minus. Now that's just working through their brains. But now they're going to look this up from a normal distribution, assuming they take thousands of German tests, and then the standard error of the outcomes of all of their thousands of German tests. Oh my gosh. Now you can hopefully see that from a statistical perspective, it's still a range. I mean, I still like that interpretation, but it's a statistical range with a level of confidence, in this case, 95%. So what we're going to say is that we have a 95% chance of generating beta 1 that's between these two numbers. That's the next step, by the way, for me to teach my children to do some confidence intervals. All right, so let's go back to our same example. There's the 95%. So beta hat sub 1, the slope coefficient is 0.6. We plus or minus 2.048, there's that critical value, times the standard error of 0.25. And there's really no simple way to do this in your calculator. I mean, the way I would do it is I would put the 0.6 in the memory, and then I would do the plus or minus on the right side, and then I would do 2.048 times 0.25, and then I would multiply it by the memory, and then recall the memory, make it positive or negative, and so you get the 0.088 to 1.12. Oh, and by the way, let me read that last part down there. When testing the hypothesis using the confidence interval method, we reject the null if the interval does not contain 0. So it does not contain 0. So all three methods, the critical value, the p-value, and the confidence interval method provide us with the same results. All right, let's go back to what we talked about, the assumptions of the OLS model. Remember, we did that IID. So we need to focus on these error terms. So notice under the condition of homoskedasticity, which is an implicit assumption inside of the OLS model, notice there's the x on the horizontal axis, there's the dependent variable y on the vertical axis, and there's the linear line, there's the black line. And then the error terms are thrown all the way around those things. So the error terms are constant, right? The variance is constant, and there are no outliers. And so just looking along those things there, it looks like that's homoskedasticity. But heteroskedasticity is when the variance changes at different levels versus x and y. And so clearly here, close to the origin, you have those terms that are pretty close to the line, right? So we start out okay, but then as we move to higher values of x, which lead to higher values of y, then those error terms that get way, way out there. And so that's a violation. Now, there are lots of causes of heteroskedasticity, but common causes are incorrect model specification and the existence of outliers. That's why it's so important, going from T to Z, that model where we worry about the outliers will have a much greater impact if you have 21 observations versus having 21,000 observations. Now, let me make certain that you understand that just having 21,000 observations doesn't remove the possibility that there is heteroskedasticity. All right, so simply in some equation form, there's the model, and the variance of that error term under homoskedasticity is constant. But under heteroskedasticity, it's not. That's why there's a subscript I down on the bottom right. So here's a good definition. Heteroskedasticity is a systematic pattern in the errors where the variance of the error terms are not constant. That's why we went that little thing there, like a bugle going out. Ordinary least squares assumes that all observations are equally reliable, but that only holds true if the error terms have a constant variance, which is homoskedasticity. All right, so here's the big question that all econometrics professors have asked their students at one time or another. So what? Do we care? Do we care if we have heteroskedasticity or not? And the answer is, yeah, we sure do. And here are the reasons. Now, the estimators, the intercept and the slope coefficient, they're still going to be linear, and they're still going to be unbiased, but they're not going to be inefficient. And the reason that they're not going to be inefficient is because when heteroskedasticity is present, there are incorrect standard errors that are calculated. which means that all of the hypothesis tests, the T and the P and the confidence intervals, are not going to be reliable. They are going to lead to incorrect conclusions. And remember, this is the last thing we want to do is collect all this data and then make a conclusion. And then let's suppose that we're a politician and we're in charge of running, water conservation. And we do all this and we say, oh my gosh, our model says that we have to require people to put fluoride in their water. Oh my gosh. But if there's heteroskedasticity, then that conclusion could be wrong. Interestingly enough, we moved from one part of the county in which we live, which had fluoride in our water, and now we don't have fluoride in our water. My children had 3 cavities at their last visit. How about the Gauss-Markov theorem? This is the blue that I talked about in that very first slide. If the linear regression model assumptions are true and accurate, and the regression errors display homoskedasticity, then the OLS estimators, primarily the slope coefficient, will have the following properties. It will have the minimum variance. That means it's the best. It'll still be linear. There's the L. It means that they're going to be unbiased, and that means, and look at that third blue box there, the expected value of beta hat 1 is going to be equal to the true value of beta. That means it's unbiased. And then the estimate of the variability, in this case the variance of the errors, is unbiased. And that means the error terms are unbiased. So blue, the best linear unbiased estimator. Now, here's the problem, that error terms are very common to contain heteroskedasticity, especially when using economic data. When I wrote my dissertation hundreds and hundreds of years ago, we had to do tests for heteroskedasticity, and then there are ways to correct for it so that you can still make some reasonable conclusions about it. And one of the ways to do this is the weighted least squares estimator, although my econometrics professor was much more in favor of the generalized least squares estimator, because you then get all the variance predictions and then you get all the covariance terms. So weighted least squares does it, but also generalized least squares estimators will do it. Now here's the problem. Remember, the t distribution is appropriate when the sample size is relatively small, less than 30. So in order to use a small sample size regression model, we must assume that the assumptions of those models hold true. So we must assume that the error terms are homoskedastic. And that takes us through this chapter 7. What we'll do next then is we'll go from one x variable, one independent variable, to multiple independent variables.